Hey folks, welcome. Sorry we're starting late here. I'm just trying to figure out how all this Teams technology works. Looks like I'm not able to see attendees in here, which is going to make things a little strange for how do I pick someone to win one of these super awesome drink coasters that I've got, as well as another super awesome Cosmos DB sticker. So we'll have to see how that works. We'll figure that out maybe for next time here, I guess. But since we've got attendees in, why don't we get started? And welcome, everyone. My name is Mark Brown. I'm a program manager on the Cosmos DB team. I know virtually here attending are other organizers that are part of this user group. So we came up with an idea to start a virtual user group maybe 4 or 5 months ago and organize it with a number of Azure and data platform MVPs located all over the world. And every month we hope to bring to you a new edition of our user group meetup with new content, the ability to be able to share with you. Hopefully we'll be able to do a drawing and can send you swag as well. And overall, just try and build a healthy Cosmos DB community that you can share with, learn from. Feel free to start discussions on the Meetup page. I think if you're here, you're all familiar with the page that we've got here. I'll put this out here. Here's the Meetup for today. But feel free to start discussions on here if you have things you want to talk about and anything else. I just want to try and provide a center of gravity for us as a community to get together and share and learn, and hopefully you all find this valuable. So let me get started, and we'll kind of see where this takes us here, huh? All right. Let me work through slides here. All right, so today we're going to talk about data modeling in Azure Cosmos DB. Here, let me put my camera back on. There we go. Hope you find this valuable. In today's session, we want to cover on about 3 major things here. First, I want you to get familiar with kind of Cosmos DB core concepts, if you're not familiar with them, and understand data modeling best practices. We're going to apply them to a near real-world scenario. We're going to take the AdventureWorks 2017 database, and we're going to model that in Cosmos DB. And hopefully along the way, you're going to understand how Cosmos DB is different than relational databases. Why is it designed the way it is, and how it works. And we'll use that evolution of our data model to help get you there and teach these concepts. So let's start with the basics. So what is Azure Cosmos DB? Well, officially, it's Microsoft's NoSQL database on Azure. But what does NoSQL mean? Well, fundamentally, it means that the database is both non-relational and horizontally scalable. So let's break that down a bit. Let's talk about the horizontal scale aspects of Cosmos DB. So unless your workload is really small with a low amount of data and request, your data is likely going to be spread across these multiple different servers, physical servers. And we call these things partitions. And also including contains within, or also include the notion of a container that is essentially a logical wrapper around these physical partitions. Now, we abstract all this away so you don't have to understand any of this, but fundamentally, you are reading and writing data across a cluster of servers. And this is better known as scale out. And the nice thing about this is when you scale out, you essentially get theoretically unlimited storage. So you just simply add more servers or more partitions to your cluster, and you get more storage as part of that. Because each of these different pieces of compute, these servers also can, has their own processing and CPU and I/O and network and all that. You also get additional throughput to be able to handle requests. So this is good because you get additional compute power as you add more servers as you scale out. Now, Cosmos DB is also non-relational. So when you work with relational databases, you have the ability to define things like relational constraints, foreign keys, all of these different things that allow you to do things like perform joins between different tables. In Cosmos DB, we don't have any of these types of relational constraints. Now, you may ask why. Well, the reason is because Cosmos is horizontally scalable. Again, your data is going to be spread across multiple different servers. It could be tens, hundreds, a lot, depending on how much storage and throughput you need. Now, I don't want to suggest that it's not technically possible to be able to implement these kinds of constraints. But what you're talking about is essentially putting things like distributed locks across different pieces of compute. And this is somewhat at odds with one of the design goals for Cosmos DB, which is high availability. Say one of those different nodes is having some network connectivity issues and you try to implement a lock, or you put a lock on it and it's no longer responsive, you're going to lose availability. Also, being able to do these types of things over a network is going to introduce latency, so performance and timing is also likely or could potentially be impacted as well. Cosmos fundamentally is designed to have predictable performance, and so for these reasons, we don't implement these types of relational constraints and other types of things for a database like Cosmos. So at this point, you may think, well, is Cosmos okay to use for relational workloads? And the answer is absolutely. In fact, most workloads are actually relational in that sense. You just need to use different techniques to implement the relationships for a database like Cosmos. Now, this is a very different approach that you're going to use and what I'm going to show you today. And it's frankly not intuitive. And if you're new to this type of database, you should not follow kind of your instincts for what you've maybe learned or likely learned using relational databases in the past. In fact, these may even be anti-patterns for designing a scalable data model for a database like Cosmos. So, as I mentioned, we were going to take the Adventure Works 2017 database, and here it is. So I'm going to spend the rest of this session taking this relational database, or at least a subset of it, and then we'll kind of go through there and remodel these. So each of these tables kind of represents the kind of canonical e-commerce workload, if you will. We've got a customer table here, so I've got our customers as entities, so I've got a customer table. We've also got a customer address table and then a customer password. And you can see I've got a one-to-many relationship from customer to customer address, and then a one-to-one relationship between customer and customer password. We've also got products, so I've got a product table here, also a categories table, so a one-to-many relationship between that and products. And then we also have product tags. So here we've represented a many-to-many relationship between the product tag, product tags, and then products itself. And then last we have sales order. So we'll have a sales order header table here, and that has a one-to-many relationship to the sales order detail, which is going to contain all of the orders, all of the items within a sales order here. Now, something I want to point out is that in a relational database, the relationships between the data is essential for modeling the database. For a NoSQL database, this is really only part of the story here. What's most important when designing a data model for a NoSQL database is understanding the access patterns for that application. And as I'm going to show you through this talk, we're going to continually go back to asking ourselves, what are the access patterns for the data in this application, and then use that to inform what we want to do in terms of design for this database here. Okay, so a real e-commerce application would likely have a lot more different methods or different access patterns for here, and we would implement more and more of these. But I think right here is really kind of the essential ones that we're going to focus on for this. Plus, I've only got about an hour or so, so we couldn't spend all day going through this. But this is going to be essential, identifying these operations that our application is going to do for really being successful in terms of designing a data model for your application. So let's kind of go through each of these, and we'll talk about them as we go through the rest of this talk. So for customers, we want to create a customer and edit a customer and then retrieve a customer. For product categories, kind of the same operations there. We want to create, edit, and list all product categories, so a little different there. We also want to create and edit and list product tags. We're going to create a product, we want to edit a product, and then we want to list all products from a category, and that would include the name of the category and also the tags for that. So I'm making an assumption here that customers are going to want to, say, navigate navigate by categories and then view all the products within that category. So that's kind of a specific use case I just want to call out. You would obviously in a real world application have many more ways of getting at those product pages, but I just want to show you this one here. And then also we want to create a sales order, of course. That's what we're all about here in this application. List all sales orders for a customer. This is a frequently run operation where I'm a customer, I'm going to go in and I want to see all my recent orders or all my orders within there. And then we'll do something maybe more analytical. So I'll do a query top 10 customers by the number of sales orders. So that's going to be all of the operations we're going to focus on here. And we'll go through this talk and let's basically go and model our data. Okay, so let's get started. We're going to start with the customer entity. And as you would expect, we're going to talk about each of the operations we're going to do. So we're going to create a customer, we're going to edit a customer, and we're going to retrieve a customer. So first thing we need to do is we want to translate each of these tables into a corresponding JSON document. Now, we could keep these in separate containers in Cosmos, but let's look at what operations we need to support. And this both includes in creating a customer and editing a customer and then retrieving a customer. Now, given that Cosmos stores data as JSON, one of the things we could do is we could embed our address and password tables into the customer table. Now, when I create a new customer, I only need to insert data into a single container. Reading data is also easier because I only need to read from that single container as well. So let's go into the portal and I'm going to run some queries here. Oh, I don't have these set up. Well, let's do this anyway. We're going to go into the portal and I'll show you my little database setup in here. So, whoops, all right, I got to log in again. Portal kicked me out. Okay, so what I've got in here in the portal is 4 different versions of our e-commerce, our AdventureWorks database here. And what we'll do as we go through this thing, we'll have successive iterations of it here. So in V1, I'm taking a very naive approach. I've got all 8 of the different tables from AdventureWorks, and I've created 8 different containers within here. So I've got my, where is it? Oh, I'm missing my customer table. Oh, that's odd. This is not right. Okay. How's this looking? Okay. Huh. That is not going to work. I better use it. Well, hopefully that works for my demo here. Well, what I was going to show you is I was going to create a query to show you getting the customer address and then also getting the customer password and then also getting the customer. And then I was going to show you what it looked like to run it in code. But since that's not quite right, let's just move on here. A little snafu here. So let me move on. At this point, people often ask, when am I going to embed data versus when am I going to reference it? And there's actually kind of some simple rules of thumb that you want to use when you want to embed data within a data model, within a document, or when you want to reference it. You generally want to embed data when there's a one-to-one relationship, or what we call a one-to-few relationship. Now, one-to-few may seem strange if you're used to, say, relational databases, but what in a NoSQL world, what we mean by one-to-few is that there's a one-to-many relationship, but that relationship is bounded, if you will. A discrete example here with customers is a one-to-one relationship would be our customer entity and our customer password entity. There we've got one customer, one password, one salt, or one hash in there for the customer. A one-to-few would be the customer and the customer address, right? You don't have an unlimited number of addresses per customer. You're going to have a handful of them. You're going to have maybe your home address, your office, your mom, your dad, your aunt, your uncle, your kids. There's only going to be just a few of them in there. So that's another one where you could go and you could embed that within the customer document. The other rule is that these items are queried or updated together. And this makes sense because in a NoSQL database, if you can embed that into a single document, you can retrieve all of the data that you need with just a single request. And that's going to be faster and consume less resources. And in a scenario when you want to try and build something to scale, that's an objective you want to go for. So that's when you embed. To reference, there's some different rules. You generally want to reference when you have a one-to-many relationship, but especially if it's unbounded. Good example of this would be maybe a blog platform. So if I've got a blog platform and I've got a container for post, I would not want to embed comments within that document for my post. I could write a really popular blog post, or it gets, I don't know, goes viral on Slashdot or whatever, and pretty soon I'm going to blow up my document with all of those different comments in there. And what's worse is that each time someone adds a new comment, I'm updating an increasingly growing document, not very scalable. So better is to add that as a separate document within there, and then you reference it with the parent document in the post for that example. Many-to-many relationships. So in the example of our product tags, this is something you would handle by creating a separate document and then referencing it. And then also when related items are queried or updated independently. I can give you a discrete example where, well, not discrete, but what I can say is if you have a document where you have an asymmetric update pattern. So you have some properties. I can give you a good example. So let's just say I have a customer entity. I have the name, the address, the email address, and some other information in there. And then I have, say, number of orders, total number of orders, which actually we have in here. Depending on how often you do that, you may want to separate that and put that into a different document. So where you have highly asymmetric access patterns to that data, and there's a large number of them, typically you will want to separate and put the static properties into one document and then the ones that update frequently into a separate document. And because that's typically going to be smaller, it's going to be less expensive in terms of updating, and you're going to get better latency as a result of that. Okay. So because we have this one-to-one and one-to-few relationship between our entities, and because we usually retrieve all this data at the same time, it makes sense to embed customer addresses and password all into the same JSON document. So now that we've defined our first entity, we need to store our customers, and we'll put it in a container called customer. Now, when we create a new container, we need to define its partition key. And you may be asking, well, what is a partition key? Well, remember earlier I referred to CosmosDB as a container and an abstraction over these physical set of clusters. When storing documents in a CosmosDB container, these documents end up being dispatched to different physical servers. So the question is how do I decide which physical server this document should go to and which physical server some other document should go to? Now, technically, we're not really assigning documents to servers. Instead, these documents are being written to these logical partitions. And it's these logical partitions that sit on different physical servers. And depending on the size of them, we'll move them around and split them and other stuff, just so that they can fit within each different logical or each different physical partition. So from a user's perspective, you don't really need to care about the underlying physical server. The only thing you need to know is just these different logical partitions. So how do you decide which logical partition a document should go to? Well, that's where the partition key comes in. So when creating a new CosmosDB container, you define the partition key, and then that partition key, which is a property in the data, decides where to route your data and how to access it. So to use the example of container partition by username, We end up with these logical partitions where, with data, where I've got a username equals Andrew, or username equals Deborah, or username equals Mark, or Tim, or Theo, and so on. So next, there's two constraints that you have to keep in mind when designing your data model for Cosmos DB. The first is that each document has a maximum size of 2 megabytes. Remember before when I mentioned about when to embed versus when to reference. This is why we don't want unbounded arrays, or one reason at least why you don't want unbounded arrays within a document is because if they keep growing, they could hit this 2 megabyte size, and then you're going to start throwing exceptions when you try to update that document. It's also not efficient when you want to update a document frequently. In fact, the cost for throughput when you update a document does not go up linearly as the document grows. It grows at a much steeper rate. So it's not efficient. You want to work with documents that are generally going to be smaller, and then also you want to separate those from those that update frequently and those that update separate or at a lesser rate, if you will. The other constraint to keep in mind is that each logical partition is also 20 gig in size. So I can't have a logical partition of, say, Andrew with more than 20 gigabytes worth of data. So when working with data, we want to try to achieve this even distribution of data across our logical partitions. And when you don't get this, you end up with what we call a hot partition. And you generally want to avoid that. In fact, you definitely want to avoid it. Same goes for the request as well. If all or most of your requests are hitting the same logical partition, this is going to be a bottleneck that's going to drastically limit the overall scalability of your model. Keep in mind, when you provision throughput, we are going to evenly distribute that across all of the physical partitions and the logical partitions, or the data within those logical partitions that sit within them. So I'll give you an example. One of the things you may want to avoid if you have a, say, a write-heavy or a high-scale application is using something like date for your logical partition. And you may say, well, why? And the reason is because if you were partitioning by date, likely the current date is always going to be your hot partition. So you're going to end up with a scenario where you may have an even distribution of data from a storage partition, from a storage perspective, but from a throughput perspective, you're always going to be bottlenecked on that current date. So what you want is you want something that's going to distribute both the storage of your application as well as the throughput or the request from a read and write perspective across all of those different logical partitions. So partition key plays an important role in terms of both the performance and the scalability. So let's take an example where we've partitioned by username here. So I've got this query, select star from C, where C.username equals Mark. And thankfully, that's our partition key. So our query knows exactly where to route the data. That's good. It hits one physical server. We're always going to have a good performance when we just hit a single physical server or single physical partition for our data. Now, let's take an example where we don't use the partition key in our query. So here I've got a query, select star from C, where C.favorite color equals orange. We don't know where to route this query. As a result, we have to hit all the logical partitions to find the favorite color equals orange, which means we have to hit all of the physical partitions. And as a result, the throughput cost and the latency on this is going to be quite high. Now, one of the things I want to point out is something that's somewhat insidious, I guess, about NoSQL databases is that you could design something and not know whether or not it's going to scale until it gets to be super large. If you're just designing and testing at a small scale, so let's say you've only got 1 or 2 physical partitions, and you're testing to see what's the cost and latency for your queries. If you're only hitting 1 or 2 logical partitions, you're not going to see the full impact of that. It's not until you get to where you've scaled out to a very large size that something like this, like a fan-out query, may reveal itself to be something that's non-scalable. I mean, in general, you want to try to avoid high concurrency queries where you're going to do fan-outs like this. Now, I don't want to say that every time a fan-out is is something that you want to avoid in some cases. In other cases, at least if it's bounded, you can get some parallelization, I guess, going on, where you can a query could get dispatched onto these different physical partitions and then go and retrieve that data. But by and large, for high concurrency queries, you want to try to design your queries and your partition strategy such that it can be answered or served by one or a bounded set of partitions in there. So just something that I wanted to call out to you. Okay, so let's keep moving here. All right, so we've got all this knowledge of our partitioning. We need to choose the right partition key for our customers. So let's go back to looking at our access patterns, right? It's always going to come back to this. We have three things we need to do. We need to create a customer, we need to edit a customer, and we need to retrieve a customer. And in this case, we're going to do it by their ID. So, and it's going to be a high volume operation too, right? So create a customer, not going to happen too often. Customers don't typically edit their data, but customers, the retrieve on a customer is going to happen every time they log in to your website, right? To our e-commerce website. So this is going to happen quite a bit. So I think for that reason, ID is going to make a good partition key for our container here. Okay. Now, one thing I want to note is when using the ID as a partition key, we end up with as many logical partitions as there are documents in the container. And each partition contains just a single document. And this is actually perfectly fine. Many users, or some users at least, are worried about having a high number of logical partitions, but there's no need to worry about this. Logical partitions are a virtual concept, and Cosmos DB co-locates them onto the same physical servers and then moves them depending on storage needs on each of these different servers. So there's no upper limit to how many logical partitions you can have in a container. And fundamentally, when you use ID as your partition key, you end up with functionally a key value store within Cosmos. So if you wanted to use Cosmos and don't need any of the query capabilities in there, you could easily use Cosmos as a key value store, and then just set the partition key to ID within there, and then you get one document for each logical partition. Okay, so let's get to some demos. That was a lot of slides in there. So in this demo, I'm going to show you a query by customer ID, and then I'll show you the cost of that, and I'll show you the code as well. So if you're not familiar with using our SDK, and I'll show it using our .NET SDK, you can see how this works within there. So let me bail out of slides, and let's go to, whoops, I just launched. Am I in the right thing? Sorry. Yep, there we go. Let me move this over here. And I've got a little app here I'm running with some menu items here. I'll show you the code for all this, where it's at. You can get it, download it, clone it, set it up, run it, check it out. And then I have a little change feed running down here, and I'll get to that a little bit later. So let's walk through some code here. I'm going to run this option A, query for a single customer, and I have a function here that shows querying for a single customer. So let me walk you through some code. So I have a shared static database client, Cosmos client instance that I'm running in this application here. It's all warmed up, ready to go. First thing I'm going to do is I'm going to get my database reference here. So that's database v2, and then I'm going to get a reference to my container. Now remember before, let's go back and look. In our database v2, I've got my customer here, right? And so this is my embedded addresses array in here, and then my password within here. And so I'm going to go and run a query to grab a customer out of here. So here's my customer ID. Here's my SQL query. So select star from C where c.id equals @id. And then I'm going to build my query here. So I'm going to call this get item query iterator, create a new SQL definition, pass in my SQL string, create a parameter in here, pass in the customer ID value, and then I'm also going to set my request options and then pass in my partition key value. Now, I don't have to do this, but I find it's a good best practice. It also helps better document your code and to document your design, because now I can look at this and say, okay, this container is partitioned by customer ID, so that's good. I can look at my code and see what my partition key is. So that's building the query there, and then I will go and run this while loop here. It has more results, and then I will just call read next async, and then for each customer I get back, and there's only one, I'm just going to print that out, and I'll print out the output of that into my console app here. So, and also I'm going to get the request charge here. So in the response object, I can get lots of different stuff, but the most important for here is getting the request charge, so I can show you that as well. So we'll run option A here, and this may take a second to warm up. It's been a while since I run it. And there we go. So I've got my customer here, their ID, their title, their name, email address. Here's the address in here, and then their password. And then I can see here's my query request charge, 2.83. So this is pretty good, less than 3 RU for my query. So that's good. Let me then show you something else, and that is in scenarios where I'm partitioned by ID and looking up a single record, I can do what's called a point read. And let me show you that. So here's my query customer function here. Let me show you get customer. So very similar at the top, I'm going to get the same database and container reference, same customer ID. However, instead of building a query with a parameter, I'm going to call this function called read item async, and then I'm going to pass in my customer ID for the ID value, and then my partition key, which is also customer ID, for that value as well. And then I'll just go ahead and print the resource from my response object, and then I'll print the request charge as well. So let's run that. That's going to be option B here. And you can see, I mean, it came back faster because the connection was warmed up again. But these will always run faster than an equivalent query. And the reason is because a read item async avoids our query engine altogether. So there's no interpreting the query that's passed in. There's no processing of anything there. It goes directly to our backend, at least if you're using direct mode, which I am here, and fetches the data. Now, I talked earlier about the partition key. So partition key is used to help route where that data sits physically on a server in there. Within the SDK client, we maintain what's called a partition key range. So we know where data is physically stored depending on the address range or the hash of the data that you're storing. So there's a hash of my customer ID that is basically, it knows, okay, the range for these hash values are going to be stored on this physical server, and then this range for hash values is going to be stored on another physical server. So when I see that request come in, it's going to say, I know where you're located. I'm going to route that request to that physical server or that physical partition, and then go get your data, right? And then it's going to use the ID essentially as kind of the lookup. And you can think of it as like routing a request. Let's say you're a pizza delivery guy, and I've got 4 different buildings, and my building number is the partition key, and the unit number is my ID. So I can get there more efficiently if I tell you the building number I'm in and the unit number I'm in, rather than I just tell you which unit number I'm in, because then I'd have to go to all 4 buildings to go and find you. Okay, so that is our first demo here. Let me go back to slides. Right. Okay, next up, let's look at our product table. So first up is the product category table. We're going to do the same thing we did earlier, which is we're going to translate that into a JSON document, and we're going to store that into a container called product category. Next, we need to figure out what our partition key is going to be. So again, we'll look at the requests we need to support in our app. So here we need to create a product category, edit a product category. And we also need to list all product categories. And again, I want to point out that we're looking at operations you need to support, so it's important to understand the volume of those operations as well. We probably aren't creating or editing product categories very often, but we're definitely probably going to list all product categories quite frequently. Granted, we would probably cache this, but it's still one of those operations that's going to get called much more frequently. There's another issue here, however, which is we have this query, but there's no filter on it. There's no where statement on it. So how do we make this a single partition query? Well, the answer is to use a little trick that we can apply here and create a new property and give it a constant value in our document. So here I've created a new property and I've called it type, and then I've given it this constant value category. And I'm going to set this value for each product category document within this container. Now I realize this looks kind of ridiculous, but later on I'm going to evolve this model and iterate on this design, and you'll see how this actually makes sense. And there's actually a reason why I'm doing this, but for now, just trust me, this is going to make sense. Okay, so in this demo, I'm going to show you the query for product categories, and then we'll measure its RU charge in our application. So let's dump out of slides here. So I've got list all product categories here, and same code at the top. Here's my query, select star from C, where C type equals category. And then I've got my query. I'm going to pass in the constant of category in there, and then we'll iterate through all of those and then print a request charge on that. So that's going to be option C, list all product categories here. And we've got about 37, I think, categories, if my memory serves, on AdventureWorks. And here you can see, here's our request charge of just a little over 4 RU on there. So efficient and works for our needs here. Okay, let's go back to slides. Oops. Okay, next we'll look at product tags here. I'm going to apply the same process here by defining a JSON document. We're going to store it in a container called product tag. Again, we got to look at our access patterns here. What are we going to do? We're essentially going to do the same thing. So let's just apply the same strategy. We're going to create a type property here, give it a value of tag, and then that's going to be my my partition key is going to be type for this container. Okay, next let's look at our product table here. First, translate to our JSON. And next, I want to look at the relationship to the product tags table. Our product table here has a many-to-many relationship with tags. And I need to access the product tags in my application, meaning that when I display a product, I also want the tags to appear there as well. And at some point, I may want to be able to query for a product using tags, although we're not going to go through that here. But being able to do that is something that I may want to be able to do in the future. Now, I could do this in one of two ways. I could store the product info in my product tags table, or I could materialize the tags in my product table. So now, given that there are much fewer tags per product than product per tags, it makes sense to materialize the product tags and embed them in my product table. Remember, too, there's a one-to-few relationship between product and tags. So this too makes it a good candidate for embedding within there. So here you can see I've got an array of tag IDs and I've embedded that within my product table here. Next, we'll store it in its own container and we'll just simply call that product. Next, we need to figure out a good partition key. So again, we'll look at the operations we want to perform here. Of course, we need to edit a product, or create a product, we need to edit a product. But the interesting one here is we want to list all products from a category, for a category, and then I also want to include the name of the category and the tags. So we're going to need something like this. So I want to select star from C, where C.category ID equals category A, and this will return all products for that category. So in order to make this a single partition query, we'd need to have all the products from that same category sit within the same logical partition. Okay, so category ID is, I think, going to make a good partition key here, and it'll allow us to retrieve all the products for that category pretty efficiently. I have another problem here though, and that is every time I query for products in that category, I get a category ID, and then I get a bunch of tag IDs. But what I really want to do is I want to display the category name, and I also want to display the tags as well for each of the products. So how do I do that? Well, I've got to, I guess I'm going to have to run a bunch of different queries. So I've got to first issue this query, select star from C, where C.category ID equals category A, and that's going to give me all my products. Next, I need to go to my product category table, and I need to, or my container, and I need to go get the name of that. So I've got to issue another query there. And then for each of the tags I've got within there, I need to then go and run iterative queries on my product tag container and get all those. Now, you may be thinking, okay, yeah, sure, just do that. That would work. But how about, couldn't we just use joins in there? Well, no, you can't actually. When working with these non-relational types of databases like Cosmos, we want to optimize our data because we don't support joins across containers. Data that's modeled in this type of data store is optimized, or at least you want to try and optimize it so that it can be served with a single request to the database. So in our products table, we're going to add some additional properties, and that includes the category name here. And then we're going to add the tag name for each of our tags within the tags array here. And by doing this, we ensure that every time I run a query by a category ID, I'm going to get back all the products, the category name, and all the tags, and do it in just a single request. Okay, so let's see what that looks like. I'm going to do a demo here, and we're going to query by the category name and then get the tag names back. Okay, so back to code here. So I'm going to call this query products by category ID, and then let me show you the code in here. So here's my category ID here, and that category name is components and headsets. And then here's my query here. And by the way, I'm getting a new container. This is the product container this time. And by the way, we're also in version 3 of our data of our database. So we're slowly moving one step further, evolving our data model here. Okay, here's my query code here, and I'm going to pass in category ID, and then that's of course my partition key here. And then we'll go ahead and iterate through those, show all the products, and then I'll show you the request charge. So let's run option D here. And well, that's a bit of a mess, isn't it? Let's see if I can clean this up. Okay, so let's print out the products, and we've got category name of components and headsets here. And here you can see I've got my products. So I've got my SKU, the product name, the description, and then here's my array of tags. So I've got my tag ID and tag name for each of the 3 tags with this product. And then tag array, tags for this product here. This is the HL headset. And then my third one is the LL headset, and I've got a bunch more tags down here. And here you can see this is pretty efficient, less than 3 RU to run this query to get all the products for that category. So this is good. I think we can be pretty happy that this is a pretty efficient design for our database here. All right, let's go back to that. All right, I wish I could see if there were questions in here. I really don't like this format. Maybe we should use, I don't know, something else, Zoom? We'll see. We'll see, folks. We're slowly, whatever, not gonna be tripped up by technology, right? Okay, moving on. Okay, so now when we create a new product, we need to populate these additional properties, right? So we've got, but a question we've got is, how do we keep everything in sync within here, right? So like I've got my product category and my product, and those are now embedded in, or product tag, those are now embedded in my product container. So how do I manage the referential integrity between containers? Because maybe I changed the product category name. Maybe I changed the name of a product tag. How do we handle that, right? We don't want these things to get out of sync. Well, as it turns out, CosmosDB has a really elegant way of being able to handle that, and it's called change feed. Now, change feed is an API that lives within every Cosmos DB container. Actually, technically, it lives within every physical partition, but we're not going to go too deep into that. What's important to note is that whenever data is written into Cosmos DB into your container, such as an insert or an update, change feed can stream these changes to a delegate, to an API that you can listen to, and then use that to respond to the data that was changed. So in our case, we have to listen to changes that occur on the product category container, as well as changes that occur on our product tag container. And then every time those changes occur, we need to propagate that change to the products container accordingly. Okay, so in this demo, I'm going to show you how to use change feed to do this. First, I'm going to query the product container for a specific category and see how many products are in that category. And then I'll update the category's name to a different name in the product category container, and then show how change feed handles those changes and propagates them to every product for that category. And then we'll change it back again too. Okay, so yeah. Let me go back to here. All right, so first thing, we showed you this one before, query products by category. What I want to show you is update product category. So we're going to change the name of a product category here. So I've got my product category container here that I'm going to get a reference to. And here's my category name. It's accessories, tires, and tubes. And what I'm going to do, I'm just going to make a small change here. And I'm going to replace the word "and" within this category name and replace it with an ampersand instead. Okay, so I'm going to define my new product category here. So I'm just going to pass in the category name, of course, category type, and then just update the name to accessories, tires, ampersand, tubes within here. Next, I'm going to call this function replace item async. This is basically what you do to call for updates for data within Cosmos. And that's that. Next, I want to show you is the change feed. So I have another little project here, change feed categories. And there's a bunch of just boilerplate code on here. I guess I can quickly show you. I've got my database here. Here's my product category container. This is the one I'm listening to. And then I have a reference to another container. This is my product container. That's the container I'm going to make a change to, right? So I'm going to listen to product category, and I'm going to affect another container with that. So within there, what I want to show you, and also there's a leases container here. Leases is kind of a checkpoint on updates. So as updates, inserts, updates happen to a container, the leases container keeps a checkpoint of what was the last time you checked to see if there were any updates, and then it can roll forward anything from there every time you check it within there. And then when it does, it puts it into this read-only collection object here that you can deserialize into whatever class you want, and then you can iterate through that and then read each of the items within it. In this case, it's product category within there. So here's our builder function for this. So this is essentially what fires every time change feed reads from the leases collection and brings in any new changes if there were any. And it's also within here, you can actually take action and do something. So here, I'm going to call my update product category name, and I'm going to pass my category ID and then the new category name. And then down here, here's my function within here. So what I need to do is I need to query my products container and get all the products back for that category ID. So that's my query here. So select star from C, where C category ID equals category ID. And then I'm going to loop through all of those products in here, and I'm going to change the product category name to the new product category name that I've got. And then I'm going to call replace item async on my product container. So that's where the propagation of that change happens, right? And it's going to happen for every product that comes back from that query when I update the product category name within there. Okay, clear as mud, right? Let's go and back to here. We're going to query products for category. And that's D here. Is that right? Query. Yeah. So is that not that's not the right one? Which one am I calling here? Yeah, D. Components and headsets. Yeah. No, that's not the right one. I'm missing a function in here. Okay, let's do this. We're going to update our product category name here. And here you can see, okay, product count. I've got 11 products in here for accessories, tires, and tubes. I'm now going to update and replace that and with an ampersand. And if I looked below here, my change feed, now you can see it's picked up that change. And I've updated 11 products with my updated category name, accessories, tires, ampersand, tubes. Okay. Now I'm going to query that again, and you can see 11 products with that updated category name, accessories, tires, ampersand, tubes. Okay. Now we can change it back to the original if we want, and I want to let you just see this again. There it is. Changed, received, updated 11 products, and we're back to our original accessories, tires, and tubes. Okay. Back to slides. We're trucking along, everybody. Okay, we're on to our last entities, the sales orders. Here we go. We're going to translate these to JSON like we've done in the past. And this is obviously another good candidate for embedding, right? We've got a one-to-few relationship here. You're not going to have a sales order with an infinite or obnoxious large set of items in your cart. And it also makes sense to embed this because we can query for an entire order with just a single operation, right? We could just go and just get the sales order ID or whatever it is that we're looking up for, and get all that with a single operation. Next, we'll store it in its own container, so we'll call that sales orders. And again, of course, we're going to look at the operations here because we need to decide our partition key. So we, of course, need to create a sales order. We also want to list all sales orders for a customer, right? This is a frequent operation that you see in e-commerce platforms where the customer goes in and sees, hey, what's the orders I've done? Maybe I want to reorder something, or maybe they're looking up and they want to see where is the order in terms of tracking. And then the last one is we want to do this one, list all customers. So we're going to do select star from C, where C customer ID equals customer A. So we'll make sure this is a single partition query. What we want to do is then lock or put all the orders for that each customer in that single same logical partition. So it makes sense to make customer ID our partition key here. So before we go any further, I want to take a step back. So when looking at the containers we've defined so far, it's interesting to note that we already have a container that's partitioned by the customer ID, and that's the customer container. So could we store customers and sales orders in the same container? Absolutely, yes. In fact, not only is this technically possible, it's a best practice for a NoSQL database. Cosmos is schema agnostic, so you want to take advantage of this sort of thing because this is not something you can do within a relational data store. And it's suitable when the data shares a similar access pattern. In this case, customers and sales orders typically are queried together. So it makes sense when data shares the same access pattern and shares the same partition key. You should definitely always look to try and store those within the same container. So instead of storing these in separate containers here, we're going to store them in the customer's container. And we also need to make another change. We're going to change the partition key from ID to customer ID. And I'll also add customer ID as a property to each customer document. So now customer documents will have the same value for ID and customer ID for their partition key property. Another thing is I need to be able to distinguish between these types of data. Remember, before I used that type property for product category and tags, we're going to do something similar here. So I'm going to add this type property or a distinguisher type property, and then I'm going to give it a constant value of sales order for my sales orders, and then customer for my customer entities. And this way I can query for these separately if I want. Okay, so now that we have is a customers container where each logical partition will contain exactly one customer record, and then all of that customer sales orders within here. And so now if I want to get all the sales orders for our customer, we could simply run with this updated query here, select star from C where C dot where C dot customer ID equals customer A and C dot type equals sales order. Okay, let's see what this looks like. Go back to demos here. All right, so I'm going to do query sales orders by customer ID here. And so we're on version 4 of our database, folks. See, and we keep trucking along. So customer ID here, here's my query, select star from C where C.type equals sales order and C.customer ID equals customer ID. Create my query here. And then I'm going to iterate through that, and then I'm going to print out each of the sales orders for my customer here. So let's go and query orders by customer ID. That's F. And here you can see I've got my customer, and they've got just 2 orders. This one here, they bought a, looks like, I don't know, mountain bike, got some shorts and a logo cap. And then you have another query here. I don't know what this is. Road 650 red. I think that's a bike, especially given the price of $782.99. I'm guessing that is a bike and not like a cap or a pair of shorts. So that's our query to get all the sales orders for a single customer, and we're doing it all within all with a single query with a single operation there. All right. All right, finally, we want to look at the last request we want to serve, and we want to query our top 10 customers based upon the number of sales orders we had or they've had. Now, this request requires you to count the number of sales orders for each customer, and then sort these counts in descending order, and then return the first top 10 corresponding customers. And now, even though customers and sales orders sit within the same container, this query is not actually something I can do with Cosmos's query language today. So the solution here is to denormalize. And what we're going to do is I'm going to create a new property, and I'm going to call that sales order count. And I'm going to store that in the customer entity. So note here, my type is going to be customer. And then I'm going to basically create an aggregate for that, and then denormalize that and store that in the customer entity here. So what we achieve that is when I add a sales order here, I'm then going to update my customer record and then increment the sales order total each time. Now, one of the nice things is because this all happens within the same logical partition, I can do this as a transaction. Cosmos actually supports transactions. That's one of the things that I guess people think of just as relational databases. We can do it. But it's scoped to a single logical partition because that all happens on the same physical machine. It's when things happen on disparate servers, on distributed systems, that we try to avoid that thing. So since this all happens on the same machine, we do support it. And so now that these are supported by or support transactions, we can do that either using a stored procedure written in JavaScript or a relatively new feature in our SDK called transactional batch. And so now I could write a query like this: select top 10 from C where C.type equals customer, and then order by C.sales order count in descending order. Okay, so in this demo, I'm going to show you quite a bit of stuff. I'm going to show you how you can maintain an aggregate for sales orders in the customer record when a new order is created, and I'll do that showing the transactional batch. I'll then also show you the query for our top 10 customers in here. Right, so let's go back to here. And in my code, let's see, we're going to query for a customer and their sales orders here. So that's going to be this. So I'm going to get everything out of the container. I'm going to get a container reference. Here's a customer ID. Now here, I'm not using the distinguisher or the type property. I'm going to get everything. I'm going to get the customer record, and then I'm going to get all their sales orders. Okay. So you're not going to see c.type equals customer or sales order in here. We're just going to get everything for them. And then I'm going to iterate through this. Now, what's different about this is that before I was deserializing these things into strong types, into POCOs. When I'm doing this type of thing and I'm mixing entities, I can't do that with the results of my query. I have to do it into a dynamic type. And then I need to inspect that property, item.type, and see, is that a customer? And then if it is, okay, great. Now deserialize that into a customer object. Or if it's a sales order, great. Go ahead and add that to my orders array, right? I've got a list object of sales orders here, and then a customer object for my customer. That's going to come back. So as I iterate through each of those, I'm going to hydrate my customer object and my orders list or orders array, and then print that out, return that back to the customer here. Okay, and then next, what I'll show you is I'm going to create a new order and update the customer order total. So, well, let's see, do I show you? Let's query for the customer and all their orders. Let's do that first. So I'll show you that. That's this function I just showed you. So here you can see, here's my customer Destiny Peterson. This is the one I had before, and her address and her password. And here you can see sales order count. And each of the sales orders below, we've got, looks like a mountain bike, 42-inch, some shorts and a logo cap, and then bought another mountain bike. Looks like a bigger bike, so maybe for her husband or her friend. Yeah, let's go back to here. So that's her order there. Next, I'm going to show you creating a new order and updating the order total. So that's this function, create new order and update customer order total. And here, I've got my customer reference. Here's my customer ID. I'm going to read back, do a point read on the customer here, and put that into my customer object here. Okay. Next, I'm going to increment sales order count. So just sales order count ++. Next, I'm going to create a new order. Now I'm just going to fake a GUID, and I'm going to do that because it makes it easier for me to delete it later, which I'm going to do. And then I'm going to create a new sales order object here. So I've got my new order ID, my sales order type, customer ID, my order date, blank ship date since it hasn't shipped yet. And then within the details here, I've got a new list of sales order details, and I'm going to add a new mountain bike within here, and then I've got some more racing socks. Next, once I've got my objects all updated, I'm going to call the transactional batch. So transactional batch sits off the container object or the container resource here. So this is my customer container, and I'm going to call create transactional batch. I'm going to pass in my partition key. Remember, this is all within the same logical partition, so you have to pass the partition key. That's not optional. And then I can call all of the operations I want to do within that transaction. And here I'm going to create my new sales order, and then I'm going to call replace on my customer object, and then I'm going to call execute async, and then just check on the status code here. Now, this is cool. I love this. The other option you have is, of course, using our stored procedures, which, of course, you have to write in JavaScript. If you're not familiar with JavaScript or you just prefer doing things in code, this is probably an easier way to do this. There are some limitations. You can only do about or up to 100 operations using transactional batch, and usually for most people that'll work for them. So I think it's much cleaner code for sure. So let's create a new order and update the order total. So we saw before number letter G. I got this customer sales order count equals 2. All right, so let's create a new order and update the order total. And that's done. Now let's query again that customer. And here I can see now their sales order count is 3. There's their first order, their second order, and then here's their new order with the new mountain bike and their new pair of racing socks within there. Great, huh? And we go. So great. we've now been able to do a transaction to get that data. Let's say also you want to be able to create orders and update that, but you also need to be able to delete an order. Say you order something and you're like, oh, I don't want it. You still got to keep that sales order count in order. So you can do the reverse as well. So I'm going to call read item async to get my customer object. I'm going to say customer.salesorderCount minus minus, so I can decrement it by 1. And then the only thing I need to do is then just call transactional batch again, pass in my partition key. This time I'm going to call delete item and pass in the order ID from before, and then call replace item async with my new customer object with the decremented sales order count, and then execute async. So let's go ahead and try that. Deleted successfully, and so now query my customer again, and sales order count is back to 2. So here I've been able to maintain this denormalized aggregate and use it for my query of top 10 customers. So let me show you that. So here is my function. This is my getting customer reference, and here's the query I showed before. So getting the top 10 and then my order by with sales order count and descending order. And then we'll just loop through each of those here. It's not very complicated. And we'll call J. And here you can see customer name and then the number of orders and then a request charge of 3.27. Now, before I mentioned that you can't often tell when the performance of queries, I guess. I don't know if you noticed, but that query is a cross-partition query within there, right? It's not using the customer ID as a partition key. It's basically going across all of them and then doing a sort by on their sales. This is the wrong one. On the sales order count within there. So before I mentioned that you kind of want to avoid queries like this across partitions or fan out queries. But in a scenario like this, where maybe you run it once a month as part of, say, some loyalty campaign or whatever, you send your top 10 customers a gift certificate or something, it's okay to run these types of queries. It's just in scenarios where you have a high volume of these things. Say every time a customer hits your website, you have to run a cross-partition query. That's the thing you want to avoid in scenarios like this. So otherwise, not that big of a deal. Okay, no, go past this. So here is basically our final design. We've gone from 8 tables down to 4 containers. I've got a customer container with a customer ID partition key, and that contains a customer and a sales order entities. I have a product tag container. I have a product container, and I've got product category container within there. But we can actually make this even more efficient. Notice I've got the type for my product tag and product category. I can actually put those. Remember before I said if they share the partition key, you can merge them together. You can absolutely do that here. In fact, this pattern is one that you can use for a lot of like reference data that you're just going to look up, maybe to hydrate some UX or something like that. It's very simple and easy and certainly less expensive to be able to co-locate all of that data that you're just going to look up and reference and stick it into a single container. Also, simpler from a change feed perspective. So anytime one of those attributes or one of those entities changes, you only need a single change feed. You just want to inspect, obviously, the type for the data it is, and then go and update its related container elsewhere to maintain that referential integrity within there. So there's our final design, fully optimized. Went from 8 tables in a relational world down to 3 containers into CosmosDB. So simpler, easier, and best of all, it's scalable. So just some key takeaways. Really, when modeling data and partitioning it, identifying those access patterns is absolutely critical, and understanding the volume of those operations that are going to happen. You want to be able to separate kind of the high concurrency from those that don't happen too often. Partitioning is critical for the best performance and scalability. Avoiding those hot partitions, whether it's on storage or whether it's on throughput, making sure you have an even distribution. Materializing relationships between entities, either by embedding them or denormalizing and pre-aggregating that data. You want to really optimize around the request for your data, not the storage. That's another fundamental difference between a relational database, which was designed in 1970 when data cost, I don't know, $10,000 a megabyte, versus today when you can buy a gigabyte of data for 25 cents. It's much different. We're optimizing around the request, the compute, not the storage. So denormalizing, pre-aggregating, doing all these things, duplicating data is not a problem. You can use things like change feed to maintain the referential integrity between those things, and your application will work fine. And also just using the different methods to change feed, using the stored procs or transactional batch to help maintain that data between those things itself. So going further, I mentioned there is a repo. All of the code you saw here today is all available over on GitHub. It's github.com/azurecosmosdb/cosmicworks. I'll navigate over there and show you that. We have some new Microsoft Learn labs that take the concepts and a lot of what you saw here today and walk you through it in a lab environment. And so if you don't want to take and clone this and use resources, because it will take resources to go and run it, I do set it up so that it will use shared database throughput and autoscale, but each of those databases is going to require 4,000 RU. You can go and run it on the Microsoft Learn infrastructure and not pay anything. In fact, you don't even need an Azure subscription to run it. And you can learn a lot of the same concepts within there. Also a document, an article here, aka ms/practicalcosmosdb. That's kind of an older article we wrote about modeling a blog platform. We've also got awesome videos on YouTube/azurecosmosdb. Feel free to go check it out. I also run a weekly podcast, Azure Cosmos DB Live TV, and I have various guests on every week, and we talk about all kinds of cool stuff new to Cosmos DB. I'll just show you the repo here, and here's the repository here, and so you can quickly deploy this to, well, first of all, you can just clone it. If you want any of the code within here, all the code you saw is all within here. So feel free to take it and use it, whatever you want. The deck that I showed also is within here. I've got I have an ARM template within here. You can deploy this to Azure. This will just create the account for you. It doesn't create any billable resources, but at least you can have the account there. Clone this thing. Make sure when you deploy the ARM template, you go to the Outputs tab in the Custom Deployment Blade, and then just grab the URI and the endpoint. I output those into the Outputs tab in there, and then just save that locally in like a Word doc or a Notepad or something. Anything that you can get them into your solution. You can either put them in the app settings JSON file, or you can use the manage user secrets. I think that's probably the safer way of doing it. In Visual Studio, make sure you do it for both the modeling demos project. Let me pull that up. What's going on with my screen here? Make sure you add either to app settings here if you want. This is weird. You don't need that. You can put it in here, or you can just right-click it and use the manage user secrets, and you can stick it in there. You need it for both projects because both projects are going to require connection to the database. And then you can just press K. That will load it up. That's, whoops. Option K here will create the database as a container. So this actually is a billable, we'll create billable resources. You'll get 4 databases at 4,000 RU of auto scale. So they'll scale down to 400 RU when they're not used. So, and each 400 RU container is about $25 a month. So if you let that thing run unused, it'd cost you $100 after a month. So I've made this easier for you. You can create your database as containers. You could upload all the data to it. And then when you're all done, you can delete all the databases as containers. So it's not going to cost you anything. Or go and run the lab as well. That's this aka MS Modeling Lab. I'll give you a second if you want to take a screen cap of this within there. And then that's it. I wish I could somehow figure out how to do questions on this thing. I thought this was going to give me a way of doing it. I see a live event Q&A. Let's take a look at that, see if there's any questions in there. And I really wish I could have. Oh, there are questions in here. All right. So I see Hassan and Anonymous. Okay. This session is not being recorded. I don't know how to record this thing. We'll try this next month. In fact, I can give you a sneak peek now. Lenny Lobel, who's a Azure Data MVP and a longtime Cosmos DB community champ. He's going to host next month's user group meetup. I don't know what he's going to talk about yet. As soon as we get that all set up, we'll get it published out on the Meetup site. Where is it? Right here. So we'll get that published out here on the Meetup so that you all can sign up and check that out. It should be awesome. Everything Lenny touches is awesome anyway. So come and join us for that next month. Oh, okay, I see some questions. Is there a resource place for data modeling examples for real world use cases? I wish, Jeremy, there isn't, but it's a good suggestion. I think there are definitely some patterns where we, or at least the community or combination, could publish, best practices, or or at least kind of suggested patterns on that. It's something I know we've talked about internally. It's just finding the time to do it. But I do like that suggestion. All right, more questions. Here, I'll just publish these as I'm seeing them. Is there a certain RU cost you want to aim to be under? From Kevin. Not necessarily. It depends on what you're trying to do. And obviously, if you're just doing a point read, you want to keep that as low as possible. Point reads typically are going to be high concurrency operations. So, 1K of data and a point read is always going to cost you 1 RU in there. So, I think the key is to know the characteristics of the workload. How much is it going to cost you? How much for a certain number of users is going to cost me concurrently in terms of RU within there, and making sure that you budget for that amount. This is kind of the tricky part, is as a resource governed service, it's not like a VM where you just queue up requests and then you get increased latency. We just basically, your request exceeds or it gets throttled, gets rate limited. And then you get you have to retry it. So knowing that how much you're going to need is important. I think things like autoscale can help with that, because you can provision some larger number of throughput and then measure to see how much it is. Yes, I'm missing customer. Thank you, Lenny. Are there drawbacks in merging categories and tags in the same container? There is no drawback for doing this. You only get benefits from doing such a thing. It's cheaper in terms of storage, because if your minimum throughput for a container is 400 RU, you can add more data to that and store it all in there rather than having separate containers for that. You can also use a single instance of functions or a single project for functions and listen to that same container rather than having multiples listening to different containers. I'll publish that. Okay. Can I run this demo with the Cosmos DB emulator locally? Yeah, I can't see why not. Actually, there's well, you know what? I've never used change feed with the emulator, but I'm guessing you could. I can't see why there wouldn't be a problem with that. Okay. Well, that's it. I think. How are we doing on time? Wow, actually, almost right on time. Hour and a half. Thank you, everyone, for joining our very first user group meeting. I hope, even though I couldn't do a drawing for one of these lovely things, that you'll come back next time, and we'll figure out the drawings on there. I hope this was valuable for you. I hope you keep coming back. Please tell your friends about this user group. We hope we can make this a success and grow this into quite a community and see where it goes. So that's it, everyone. Thank you again so much for joining. We'll see you all again next month. We'll see you next month. Just go back to the Meetup page. We'll publish the next Meetup, and we'll see where we do that. But we'll have some place for you to go. Thanks again, everyone.